Good day everyone! Ever wondered how a rough mix becomes perfectly smooth? Today, we will explore the answer, which is high pressure homogenization. Let's begin. To begin with, high pressure homogenizer is a continuous flow unit operation commonly used in the food processing industry. It operates by forcing liquid food through a narrow valve or orifice at very high pressure. This process is applied to liquid and semi-liquid food systems, typically within a pressure range of 100 to 350 megapascals. During homogenization, the fluid is subjected to high shear forces, intense turbulence, and cavitation effects, which break down large particles and droplets into much smaller sizes. These allow the high-pressure homogenizer to function by producing a finer and more uniform food structure, improving emulsion stability, enhancing texture and mouthfeel, and ensuring consistent product quality throughout the food system. Moving on, for the mechanism of disruption, first, we have turbulent eddy dissipation. Here, the chaotic high-speed flow creates violent swirling eddies. These eddies tear apart particles through intense, irregular collisions. Next is cavitation and implosion. An extreme pressure drop forms vapor bubbles in the fluid. These bubbles then implode violently, generating powerful microjets and shock waves that physically smash the particles apart. Finally, shear and impact. A high-velocity gradient within the narrow gap creates strong laminar shear, stretching and weakening the particles. Immediately after, the high-speed jet collides with a hardened impact ring, delivering the final disruptive force.
Next, I will explain about the working principle of the high-pressure homogenizer. First, the liquid product will enter the system through the product inlet at low pressure. This will produce a continuous and controlled flow while preventing air entrainment and disrupts homogenization at the same time. Next, the product will then be pressured to a very high level, usually between 100 to 400 megapascal by high pressure pumping. This step is essential because it provides the pressure energy needed for effective particle and droplet disruption. Next, the pressure liquid is directed into the homogenizing valve that contains a very narrow gap. This valve will act as the main homogenization zone and control the pressure distribution and flow direction. After that, once the liquid passes through the homogenizing valve, it experiences a sudden pressure drop and rapid increase in velocity. This creates extreme mechanical stress within the fluid. At the stage of particle breakdown, shear forces, cavitation, and turbulence occur simultaneously. These forces work together to break down the large particles or globulus into much smaller and more uniform sizes and form a stable emulsion or dispersion. Finally, the homogenized product is released through the outlet at lower pressure. The resulting product has improved stability, uniformity, and is ready for further processing or packaging.
For the advantages of high-pressure homogenization, HPH, it's for perfect texture and stability. HPH creates a uniform, smooth product that prevents separation. As shown in research, the key outcome is that HPH treatment results in a more homogeneous and physically stable suspension, which is critical for products like juices and sauces. Next, for better food performance, the process improves how protein gel and emulsify, leading to a superior final texture. The article confirms that homogenization modifies protein structures, which directly leads to an improved gelatin and solubility in products like yogurt and plant-based alternatives. Finally, for natural preservation, it inactivates microbes using intense physical force, reducing reliance on heat or chemical additives. Studies support this, showing that HPH achieves significant microbial inactivation, validating its role as a non-thermal preservation method for cleaner label foods.
Furthermore, for the disadvantages of high-pressure homogenizer, first, reduced product performance may occur when samples contain high particle or solid content. Small valve and narrow channels can become clogged that reduce homogenization efficiency and potentially damage the internal components. Second, high-pressure homogenizers have high energy consumption. By generating extremely high pressures, it requires large energy input, and this will increase operational costs and cause heat generation that may require cooling. Lastly, The process involves high capital investment and maintenance requirements. The equipment is expensive and regular maintenance is necessary to ensure optimal performance and prevent contamination.
Right now, I will proceed to explain the position of the high-pressure homogenizer in the process line. This unit is mainly used for liquid or semi-liquid foods such as milk, cream, sauces, beverages, and ice cream mix. First, we have raw materials which are received, checked, and stored. Then, they go into the mixing tank where all ingredients are blended into a uniform liquid mix. After that, the mix goes through heating or pasteurization to kill microorganisms and to reduce the viscosity. Only after this step, the warm product enters the high-pressure homogenizer. Once homogenization is done, the product moves to the downstream steps, for example, cooling, aging, freezing, filling, and finally, packaging. Now, I will proceed to explain my second slide, which shows the main components of a high-pressure homogenizer and how it works. Starting from the left of the flowchart, the product first enters the machine through the inlet from the balance or mixing tank. It's then pulled into the high-pressure pump, which is usually a piston or plugger pump that compresses the product to a very high pressure. From the pump, the pressure product is pushed into the homogenizing valve, where it is forced through a very narrow gap between the valve and the valve seat. Here, the velocity becomes extremely high, and the intense shear and turbulence break the fat droplets into much smaller, uniform sizes. After leaving the valve, the product passes through the cooling system, which removes the heat generated during the homogenization and keeps the product at the desired temperature before it continues to the outlet and flows to the next processing step. On the right side of the slide, you can see the pressure gauge, pressure relief valve, and control panel and frame, which are used to monitor the operating pressure, protect the equipment from overpressure, and control the overall operation of the homogenizer.
I will explain the main external components of a high-pressure homogenizer used in food processing. First, the robust mounting. The homogenizer is mounted on a stainless steel frame or skid, which provides a strong mechanical support. This design ensures durability during high-pressure operation and also allows ease of movement and installation in industrial processing lines. Next is the inline connection. The homogenizer is strategically integrated into the processing line. At the inlet, it receives product directly from upstream equipment such as pasteurizer, ensuring continuous processing. At the outlet, the homogenized product is directed to downstream equipment like a cooler or aging tank, helping to maintain product integrity and consistency throughout processing. Finally, we have the essential utilities. A stable electrical power supply is required to operate the motor and control panel. Cooling water is also used to regulate temperature during homogenization, preventing heat damage and preserving product quality. In addition, the clean-in-place system or CIP allows internal cleaning without dismantling, ensuring hygiene and operational efficiency. For the next slide, I will focus on hygienic design and safety features. First, material compliance. The homogenizer is constructed from food-grade stainless steel, which is corrosion-resistant and essential for food safety regulations. Second, CIP process integration. The system supports a complete cleaning cycle, including rinsing, detergent application, and a second rinse, and lastly, sanitization, ensuring removal of residues and microorganisms. Third, enhanced safety features. These include a pressure relief valve to prevent overpressurization, guards on moving parts to protect operators, and emergency stop buttons or interlocks for immediate shutdown during emergencies. Lastly, the design features. The equipment incorporates smooth surfaces, rounded corners, and full drainability, minimizing contamination risks and improving cleaning efficiency.
For this slide, I will explain about internal components of high-pressure homogenizer. One of the components is high-pressure pump. It has some components too that play their roles for functioning of pump. Firstly, electric motors supply rotational power to drive the pump. The motion triggers piston to move inside the cylinder to create suction and discharge. At the same time, crankshaft and connecting pump convert motor rotation into back and forth motion. pump cylinder provides space where the liquid is drawn in and compressed. High pressure manifold will carry compressed liquid into homogeneous valve. Safety relief valve is equipped to prevent backflow of liquid. It opens only on suction stroke to let product enter. The other component is homogeneous valve. It has two built-in valves, which is one-stage valve and two-stage valve. One-stage valve is used when there is single homogeneous step. Two-stage valve is the second valve to break clumps of sample and control back pressure. Then I will explain each of the components one by one. The valve body is strong and hard enough to contain high pressure liquid. Liquid enters through inlet passage and forced to go through the valve seat. Valve seat is a fixed hardened surface with a narrow opening. At the same time, valve moves back and forth inside the cylinder to create suctions. The final emulsions flows through outlet passage and experience high pressure in cavitation zone. The tiny gap, impact surface, and cavitation activity works together to create shear, turbulence, and cavitation so that the droplets size are minimized.
Next, I will discuss temperature as one of the factors affecting the efficiency of a high-pressure homogenizer. Although high-pressure homogenization is considered as non-thermal process, some adiabatic heating still occurs. A moderate increase in temperature can actually be beneficial because it reduces the viscosity, allowing the fluid to flow more easily through the homogenizer. This improves the particle size reductions and overall processing efficiency. However, excessive temperature can have negative effect. It may lead to protein denaturation and the loss of heat-sensitive material. Therefore, proper temperature control is essential to maintain the product quality, safety, and nutritional value, especially in food processing application. Another important factor affecting efficiency is pressure. Pressure directly affects the particle size and microstructure of the product. As the pressure increases, the particle size decreases due to enhanced shear force, turbulence, and cavitation, resulting in a more uniform and stable emulsion. Pressure also affects the product quality characteristic. Higher pressure can cause viscosity reductions, making pumping and filling easier. This helps save energy and processing time, and allow for faster packaging with minimum quality deterioration. However, excessive high pressure may cause problems such as overheating, protein denaturations, and degradation of heat-sensitive nutrients and bioactive compounds. Besides, this slide explains how sample size affects the homogenization efficiency. First, the initial particles play a very important role. Larger initial particles require higher pressures and more energy to break them down during the homogenization. This means the process becomes less efficiency and more costly. On the other hand, the smaller initial particles are easy to homogenize because less force is needed to reduce their size. As a result, the process becomes more effective. After the homogenization, a smaller final droplet size is desirable because it improves the texture, stability, and shelf life of the product. Smaller droplets also reduce the phase separation, leading to a more uniform and stable product. Overall, controlling the sample size is essential to optimize the homogenization efficiency and product quality.
Flow rate of the fluid is one of the factors that can affect the efficiency of the high-pressure homogenizer. Flow rate is the speed which the fluid passes through the homogenizing valve. When the flow rate is high, the fluid passes through quickly. This contributes to insufficient residence time of the fluid under shear force, turbulence, and cavitation. As a result, poor particle size reduction may happen and cause non-uniform dispersion. Homogenization efficiency will also be reduced. In contrast, if the flow rate is low, the fluid remains too long in the homogenizer. This may use excess energy and degrade the heat-sensitive components. Consequently, it affects the product quality. Therefore, optimal flow rate should be applied to provide adequate residence time for effective shear and cavitation to allow uniform particle size distribution. Besides, viscosity of the fluid also affects the efficiency. High viscosity fluid will flow more slowly through the homogenizing valve. A higher operating pressure is required to force the liquid to pass through the narrow gap. Therefore, Longer time is needed to pump the fluid and thus reduce the efficiency. Since homogenization relies on shear force, turbulence, and cavitation to break particles, these forces will be reduced in very viscous fluid and contribute to poorer particle size reduction. As higher pressure is needed to pump the viscous fluid, more energy is required. However, higher energy consumption will not always contribute to better homogenization, but can reduce the overall efficiency. Other than material factors, equipment design such as valve design can also affect the efficiency. For example, sharper seat angles can change the flow direction of the fluid. This enhances turbulence and energy dissipation, which improve the homogenization efficiency. In addition, smaller valve gaps can help to increase fluid velocity as higher shear force and stronger cavitation will be produced. This can effectively improve the particle size reduction. However, if there is poor equipment design such as an excessive small gap is used, this will increase the pressure drop and friction, which in turn reduce the efficiency of the homogenizer.
For yogurt manufactured from HPH treated milk, standardized milk is preheated and then homogenized at high pressure, typically 200 to 300 MPa, to create a very fine emulsion in which fat globules are much smaller than those produced by conventional homogenization and are densely coated with casein and partially denatured whey proteins. This processing greatly increases the total protein cover fat surface area so that during fermentation, the casein cover fat globules become active elements in the acid gel network, enhancing protein-protein and protein-fat interactions as pH falls and the gel forms. As a result, both set and sterile yogurts made from high-pressure homogenized milk show higher firmness, improved rheological properties such as higher storage modules and better water holding capacity, with reduced synersis compared to yogurts made from conventionally homogenized and heated milk with the same protein content. This textural benefits longer refrigerated storage because HPH strengthens the gel so effectively it can allow manufacturer to add lesser milk solids which is required to achieve a given firmness. For milk processed using high pressure homogenization, preheated milk is first pumped to very high pressure, typically around 100 to 300 MPa, and then forced through a narrow homogenization valve or nozzle where the liquid accelerates from below 0.5 meter per second to well above 100 meter per second, even reaching about 200 meter per second and 300 MPa. In this tiny gap, the milk experiences intense shear, turbulence, and cavitation, which rupture the fat globule membrane and break them into smaller droplets, while casein micelles and whey proteins rapidly adsorb to the newly created fat interface to form a stabilizing protein layer that prevents recoalescence and greatly reduces creaming. The rapid pressure drop across the valve generates cavitation bubbles that collapse violently, adding shock wave and impact forces that narrow the droplet size, and the mechanical energy input is largely converted into heat, increasing milk temperature by roughly 0.15 to 0.20 degrees Celsius per meter per megapascal, so that milk entering at 40 degrees Celsius may leave the homogenizer at about 103 degrees Celsius after treatment and 300 megapascal. This combination of droplet disruption and heating can partly denature whey proteins and inactivate some microorganisms, so that under suitable pressure and temperature combination, HPH potentially function as conventional pasteurization and homogenization for drinking milk, although the very high interfacial area can also make the product more susceptible to liquid oxidation and off flavors if not carefully controlled.